So recall that we have learned about the Clausius-Duhem inequality, which is a inequality formulated by taking both the first and second laws of thermodynamics into account. And we have also learned the principle of material frame indifference. We have seen what frame indifference means for various physical quantities. Now, these two together impose certain restrictions on the kind of constitutive equations that we can have. Uh, so, uh, for example, uh, consider that a quantity phi and a quantity lambda are constitutively related. That means that there is an experimentally determined functional relationship between phi and lambda. Phi can be something like stress, lambda can be something like strain, and they are related by this function. Now let this be the constitutive equation seen by the observer at O plus, and then this constitutive relation for observer, this is the constitutive relation seen by the observer O, and then for observer O plus, the constitutive relation should be phi plus, which is the transformed version of phi in the coordinate system of this observer. That means if phi is a scalar, phi plus and phi are equal. If phi is a tensor, then phi and phi plus are related by q phi, q transpose, and so on. Phi plus and lambda plus should be related by the same functional form as for the observer fixed at O. That means the functional form of a constitutive law should not change from frame to frame. This is what we mean by objectivity. For instance, suppose that we have a constitutive equation for the O observer. We have a constitutive equation which is sigma dot is related to the rate of stretch through a set of fourth order, constant fourth order tensor C. Now, for this to be frame indifferent or objective, O plus should see this constitutive equation. This should be the constitutive equation that O plus envisages. But let us take this side. Let us write this in indicial notation. So sigma dot plus mn. Let's say it's C plus mn pq d plus pq. Now we know d transforms as a frame indifferent tensor. So C plus mn pq is let's say q pr q qs drs. Now this is a fourth order tensor, so it should transform as, let's say, qmi, qnj, qpk, ql, cijkl. So this should be the transformation. Now these two, because qq transpose is I, so these two will give you delta kr. These two will give you delta SL, which will knock off this R and S and give you Cijkl dkl. So what you have is qmi qnj Cijkl dkl, which we know is from this constitutive equation is sigma ij dot. So this quantity sigma mi sigma nj sigma ij dot has to be your sigma mn dot plus, but it is not. So this is not the case because we have seen that the rate of change of the Cauchy stress tensor is not an frame indifferent tensor. So this is not the case, and therefore this does not hold in the rotating and translating coordinate system O plus. So this is not material frame indifferent or objective constitutive equation, if we had framed this equation instead of doing it in for this, if we had framed it in terms of an objective rate like the convected rate or the Jarman rate, this would have been a frame indifferent constitutive equation. Consider a plate which is at time t equal to 0, which is this, uh, subjected to a constant stress in the x direction, sigma naught, and then it rotates in this direction with an angular velocity omega about the center, um, holding the stress fixed. So this is a rotated configuration at some time t. So sigma naught, sigma at time t equal to 0 is simply sigma naught 0, 0, 0. This is the stress. And to um, find the stresses at any time t, what we have to do is we have to get the rotation tensor between these two configurations at time t, and the rotation tensor is actually the deformation gradient because this is a rigid body rotation. So F and R is the rotation tensor and F and R are the same. So F turns out to be this at time t, and with this F we can now take the stress at 0, transform it and find the stress at t. So the stress at t in the xy, original xy coordinate system is this. This is a simple transformation with this F equal to R, this R matrix. So once you do this, you can take the derivative of this, time derivative of the stress, and the time derivative would be this, which is for any arbitrary time t not equal to 0. Therefore, if your constitutive equation is of this sort, like in the previous discussion that we had, if your constitutive equation is of this type, then sigma naught is non-zero, which means that you will get a non-zero stretch rate. If you get a non-zero stretch rate, that would seem to imply that there is a stretching in this direction, which is not going to happen because this stress is a constant stress. So this leads to using this kind of a stress rate measure in the constitutive equation gives rise to a physically unrealistic situation where you get a straining even if you apply a constant stress on a body. How do we remedy this? To remedy this, as we discussed in the last segment, that we can replace this by some objective stress rate like the Jarman rate. So if we replace it by the Jarman rate, remember the Jarman rate is sigma dot minus W sigma plus sigma W. This is the Jarman rate, and to calculate the Jarman rate, we will have to calculate L. So we take this F, which is same as the rotation. So F dot is easily calculated. So omega comes out, then you have minus sine omega t minus cos omega t from this term, and so on. F inverse is also easily calculated from F, and L is, remember F dot is LF. We have derived this. So L is F dot F inverse. So I have F dot, I have F inverse, I can calculate L. Then W is half L minus L transpose. That also can be calculated once I have L. And once you have W and you have the sigma at any time t, you can calculate the Jarman rate, and the Jarman rate will come out to be 0. So if you frame your constitutive equation as Jarman rate of stress is equal to C times D, then in this kind of a situation, where this is actually subjected to a constant stress, you will not get any stress rate, you will not get any rate of any Jarman rate. The Jarman rate will identically be 0, which means that your rate of stretch will be 0, which is the physical situation that we are trying to model. So this kind of underlines why it's important to have to use proper objective rates of the stress, of the Cauchy stress in your constitutive equations. In the next problem, we will show that you can use any rate here if you like, any objective rate here that you like, but that will affect the nature of the constitutive equation that you have on the right hand side. Without adjusting for every rate that you use, you will have to adjust the constitutive equation properly. Otherwise, again, you will get unphysical results. The problem. So a body is undergoing a pure simple shear, and with time. So T is the time. So this is a simple shear, and we are told that you have a frame indifferent constitutive equation, and this rate is one of the different rates. So it can be a Jaumann rate, that is sigma hat. It can be a Truesdell rate or a Green-Nagdi rate. All of these are objective rates. So this is related to the isotropic tensor, isotropic C matrix, and D. So here D, C is isotropic. And whatever rate you use here, you use the same isotropic C, so that the right hand side is the same function of D. Right hand side is the same function of D. Lambda and mu are the same constants no matter what rate you use here. What rate you use here, Jaumann, Green-Nagdi, or Truesdell. Okay, so let us see what this yields to. So this is the motion. F is simple. F dot is, so there's T only here, so everything goes to 0, this goes to 1. F inverse is also simple to calculate. This is your F inverse. Now once you have this, you calculate L, F dot F inverse, and from L you get D and you get W. So this is your D and this is your W. So D, remember, is half L plus L transpose. W is half L minus L transpose. And you calculate, let's say first we calculate the Jaumann rate. So the Jaumann rate, remember, is this. So the Jaumann rate is sigma dot minus W sigma plus sigma W. We'll calculate from the Jaumann rate, we'll calculate sigma dot. So that would be Jaumann rate minus plus W sigma minus sigma W. Now from the constitutive equation, Jaumann rate is given in terms of D. So we know that this is lambda trace of D plus 2 mu D. D we have already calculated, so we can get the sigma dot when we are using the Jaumann rate on the left hand side. So as the rate, we are using the Jaumann rate here. That's what we have done. So for this we have substituted the constitutive equation here, and this is what we get, right? So sigma dot is now sigma x dot, sigma xy dot, sigma xy dot, sigma y dot, and that we can now write down completely because we know all of these things. We know D, we know W, so we write down the right hand side completely, and we get a set of differential equations for sigma x dot, sigma xy dot, and sigma y dot. So these are each of these are functions of sigma x, sigma xy, etc. And if you work this out, it's very simple. You will see that you will get these sets of differential equations. So these are a set of coupled differential equations which you can solve, and you can get the variation of one of these things. Let's say sigma xy. You can get the variation of sigma xy with time because we know sigma is a function of time. Okay. Uh, Similarly, we can use the Truesdell rate. So remember the Truesdell rate, we can use the Truesdell rate here. And uh, to calculate sigma dot, here we use the Truesdell rate. In place of this, we use Truesdell. And when we use the Truesdell rate, this equation will change. Sigma dot expression will change. You can work out the expression. This is the Truesdell rate. And here I have again used the same constitutive equation. So remember, I am told that whatever rate I use, the right hand side of the constitutive equation does not change. That means this C isotropic C matrix is not C tensor, the fourth order C tensor is the same no matter what rate you use on the left hand side. So I have used the Truesdell rate, but the right hand side remains the same. So for the Truesdell rate, these two terms are the same. These are the Truesdell rate terms that connect the Truesdell rate to the sigma dot, and this will again lead to another set of coupled differential equations, and here they are. You can check this out, and the important thing is that now this set of differential equations that we have got for using the Raman rate on the left hand side and the Truesdell rate on the left hand side, both objective rates, but the differential equations that we have got are different. So the solutions to these differential equations will be different as well. So I'm not going to solve this here, but I can show you the solutions. These are the solutions to sigma 1 2 or sigma xy by t, where t is the time, but we have also taken it to be the amount of simple shear that we have imparted. So this is the solution for sigma xy for Truesdell. This is for Jaumann. I've also plotted the one for Green-Nagti, and you can see that they are all different. This is of course not correct, not a physical situation, and this leads us to the fact that this is happening because we are not modifying the right hand side properly based on the rate that we have chosen. So the right hand side has to be different. The constitutive equation has to be different for different rates. So we can use any objective rate and d on the right hand side, but we have to modify the constitutive equation every time to accommodate the rate that we want to use. That's the message that this problem gives you. Now we will try to see what are the restrictions imposed on constitutive equations through the Clausius-Duhem inequality and the notion of objectivity taken together. First, let us take a problem where we look at the effect of Clausius-Duhem inequality alone. So assume that we have a rigid heat conductor. A rigid heat conductor is a body which is rigid. That means it doesn't undergo any deformations, but it conducts heat. So let us assume that we have the free energy per unit deformed volume. It's a function of the temperature and the gradient of the temperature. This gradient of temperature, we'll call it by a vector g. The entropy is also a function of the same things, and the heat flow vector is also a function of the same things. So these are constitutive relationships where we are assuming that temperature and the gradient of temperature are independent variables, and then on these independent variables, these variables are dependent. These physical quantities are dependent on the independent variable theta and gradient of theta. Now this constitutive assumption comes from some other understanding of the problem. Let's not go into that. Let us accept this constitutive relationship and see what it means to have this constitutive relationship. So one thing that this constitutive relationship must do is that it must satisfy the Clausius-Duhem inequality. And now we will talk about what it means to satisfy the Clausius-Duhem inequality. So what I have written here is the Clausius-Duhem inequality as we have derived. in the deformed configuration, because these constitutive equations are given in the deformed configuration. These are in terms of quantities in the deformed configuration. So this is the gradient in the deformed configuration, and this is the temperature in the gradient temperature in the deformed configuration. So we write the Clausius-Duhem inequality in deformed configuration. It's a rigid conductor, so there is no D. So this is 0, and I'm left with this plus 1 by theta q dot g is less than equal to 0. Now, this is the free energy per unit deformed volume. So this free energy is given by this function. So if I calculate now psi dot, that would be del psi hat del theta times theta dot plus del psi hat del gk, let's say gk dot, which can be written as del psi del theta del psi hat del theta theta dot plus del psi hat del g dot. Now take this and replace it here. So what we have now is del psi hat del theta theta dot plus del psi hat del g dot plus eta theta dot plus 1 by theta q dot g has to be less than 0. Let us club these terms together. There's two terms with theta dot, and we have del psi hat del theta plus eta theta dot plus del psi hat del g dot. Now remember, this equation cannot be violated. This inequation cannot be violated at any point of time in any manner possible. This is the second law and the first law of thermodynamics taken together. Also note that psi hat is a function of theta and g. It's not a function of theta dot. Similarly, eta is a function of theta and g, and it's not a function of theta dot. Psi hat is not a function of g dot either, which means that I can actually, in a thought experiment, I can actually vary theta dot and g dot independently of these coefficients here. So I can vary theta dot and g dot in any which way I like, and these coefficients will not be affected as long as theta and g are fixed. At any fixed theta and g, I can vary theta dot in any which way I like, which means that I can always find a theta dot at a given theta and g. I can always find a theta dot and a g dot combination which will violate this inequality. Now, in order to prevent that this inequality be ever violated, I must therefore have this equal to 0 and this equal to 0. And these two things equal to 0 will mean that del psi hat del g is equal to 0 will imply that psi hat is independent of g. We have taken it to be dependent on g, but that's not possible according to the Clausius-Duhem inequality, which will mean that psi hat has to be a function of theta alone. There is no dependence on g. So now I have figured out that this term is free of g, and therefore this has to be free of g as well, which we have already figured out that this has to be equal to minus eta. This is a function of theta, so this has to be a function of theta as well. Then we are left with 1 by theta q hat theta g times g is less than equal to 0. This is what my Clausius-Duhem inequality gives. Now think of the Fourier's law of heat conduction, which says that the heat flow vector is linearly dependent on the gradient of temperature. That's the Fourier's law. So for example, the Fourier's law can be stated as Q hat is equal to minus K times G, where K is a constant greater than 0, which is called the thermal conductivity. And now if you plug it in, this actually does satisfy the Clausius-Duhem inequality, because if you plug it in here, what you get is, on the left hand side, what you get is 1 by theta minus K G dot G, that is G square, and this term is always greater than 0. K is a constant that is greater than 0, therefore this whole thing is always less than 0, and that means it satisfies, that means this constitutive equation between Q and G actually satisfies the Clausius-Duhem inequality, so it's an acceptable constitutive equation. However, a constitutive equation which has psi dot dependent on theta and g, as we have seen, is not acceptable. It should not be a function of g, so that it does not violate the Clausius-Duhem inequality. One kind of constitutive equation that we will talk about quite a bit is that of elastic solids. So in elastic solids, the stress, let's say the Cauchy stress at a point in the deformed configuration, is given as a function of the deformation gradient and the position, the position of the point small x in the reference configuration, that is capital X. So this is the form of elastic solid where the stresses depend only on the deformation gradient, nothing else. Now it can additionally depend on temperature, but temperature being a scalar does not have much consequences on the idea of frame indifference. So we will take an isothermal situation right now. So now if you look at this, let us also assume that this G does not depend on position. It's a homogeneous solid. So just for simplicity, think of the constitutive equation as sigma being dependent on the deformation gradient at that point. Now, material frame indifference would of course require that for the O plus observer, this is the constitutive equation. So the O plus observer will measure F as F plus. The components of F plus and components of F are different, but the tensors are the same. Similarly, the components of sigma and sigma plus are different, but the tensors are the same. So the O plus observer will measure this and will assume, if we assume frame indifference, the form of the law should not change, and therefore if he measures F plus, this is how we will get sigma plus. So if he uses the correct F plus, that means if he uses QF as his F plus, he should get sigma plus as Q sigma Q transpose. So this is what should happen. This is what should happen. And then this sigma is G of F. So this is what the observer in O has measured. So Q times G of F Q transpose has to be equal to G of QF. So this is the condition that this constitutive function G has to satisfy in order for this and this to be true. Now, what we are going to do is we are going to write this in a slightly different way. So G of F will be Q transpose G QF and Q. And we're going to say that this has to be valid for any arbitrary Q, and therefore it has to be valid for the tensor R as well, where R is the polar decomposition of R comes out of the polar decomposition of F. So F is equal to RU, and for this R, or rather for R transpose also, if I take Q equal to R transpose, which is also a rotation, this should be valid as well. So if I take this to be R transpose, then I get R, Q transpose is R, G is R transpose F, and then we have R transpose here. So this R transpose F is U, and then we have R, G of U, R transpose. So what we have seen from here by making this choice, what we have seen from here, that if this G is not explicitly a function of F, but if it's a function of U, then we are guaranteed to have objectivity satisfied in this kind of constitutive equation. Therefore, we need to have a constitutive equation where sigma is a function of U rather than being a function of F alone. Now, what we have learned from the principle of material frame indifference is that constitutive equations for elastic solids need to be framed in terms of U or functions of U. So we will frame them in terms of C. Let us say that the free energy per unit undeformed volume, psi naught, is a function of C, and the temperature in the reference configuration, theta. Temperature is a scalar, so we don't need to worry much about it. So once you have framed the free energy in this way, this is the constitutive equation for free energy. We are assuming that our independent variables are C and theta, that is our sort of input to the system, and psi naught is a derived variable, is a dependent variable that is dependent on C and theta. Now, this is the Clausius-Duhem inequality in the reference configuration. We have derived it before, and we also have derived the fact that P times F dot is equal to S times E dot. However, we are writing things in terms of C, so we just use the equation E equal to half C minus I, which means E dot is half C dot. So this is equal to half S times C dot. Here, from here, we can calculate psi naught dot, which would be psi naught hat Cij times Cij dot plus psi naught hat theta dot, and we will plug it in here. We'll plug it in here. This can be written as psi naught dot C double colon C dot. Again, I will plug this into this equation. So I have theta dot here, I have C dot here already. So this C dot will club with this C dot term, and this theta dot term will club with this theta dot term, and what I will get is this. So I have clubbed the theta dot terms together, C dot terms together, and the rest of the terms are here. So now, again, we use this argument which is due to Coleman and Knoll, 1963. And the argument is the same as what we used for a rigid conductor. The argument is that this quantity does not depend on theta dot. This quantity does not depend on C dot from the constitutive assumptions that we have made, and therefore we are at liberty to vary C dot and C dot and theta dot as we want, and without varying this quantities inside the brackets. So we can vary them as much as we want and violate the second law of thermodynamics, which we are not allowed to do. Therefore, this has to be 0, so that under no circumstances should this violation take place. If this is 0, then the entropy in the deformed configuration is given by minus del psi naught del theta, and the second peak stress will be given by del psi naught del Cij. So S, the second peak stress, can now be derived in terms of a scalar potential, which is the free energy of the system, which is a function also of c alone and possibly theta. But we have to take a derivative with respect to c, and if we take a derivative of the scalar potential with respect to c, we get the second peak stress. So that is the lesson that we get from the Clausius-Duhem inequality. In case we have an isothermal situation, the gradient of theta is not there, gradient of theta is 0, isothermal, this term is 0, and then the dissipation, which is the left hand side of this inequality, the dissipation is equal to 0, which shows that a purely elastic solid, isothermal elastic solid, is non-dissipative, is completely non-dissipative. Dissipation is equal to 0, and these kinds of materials are called hyperelastic materials. And we will do a lot on hyperelastic materials and how to model them in finite elements in the coming classes.